to a new episode from your favorite artist electronist, Mr. Q12 here. I'm presenting to you a failed demagnetizer and a good one. Good and simple and cheap, and it took me one day to make it. But first I will talk about this one, because this was the initial idea I had. It's a little bit of story about it. I had this laminated core. It's actually called transformer core, or silicon steel. So transformer steel or silicon steel or steel with silicon. Silicon is a metal element. If you didn't know about it, is a special alloy specifically for transformer core and transformer steel that is conducting very well the electromagnetic field, and is not opposing, is not resistive to the electromagnetic field that is created by the coil that is surrounding this core. And this core, I had it for when I was adolescent, from when I was going outside and scrapping and finding things and scrapping things. And this was most probably was a transformer at its time, but the coil was most probably was blackened, was damaged totally. And what I scrapped, I only scrapped this core. I get rid of the wire. I took it out, and I choose to keep only this core because it was almost brand new at the time that I took it, very shiny, and without any kind of rust on it. So as you can see it here, it preserves itself. It's getting a little bit of dirt or something, but so originally I had it here. I had it in this little drawer here. This is a part of this core, because this is an A core and this is the I that is over that A core. So I had it for a very, very long time. This only this core with A core and I core, and I never had any idea what to use it for. And I knew in my back of my mind I have it, but I didn't know what to do with it. I just keep it there. Actually, I had a very big problem, like you are saying here, that I am. You see this shit? Do you see this shit? How it magnetized everything. Actually, I purposely magnetized everything, quite hardly I may add, and everything, all the needles are magnetized by themselves. So they have a lot of magnetic, you see, power on them. They have a lot of magnetic field on them, and also this one, and also this one. Actually, I'm working all the time with this, especially with these two instruments, and when I'm getting into very thin metal pieces, scrap like this, like I'm having here, you see. If I will get in there, everything will stick to the tweezer. So right now, everything that you are seeing here is magnetized purposely, because I wanted to show my demagnetizers that I built. And all the time I'm using them and I'm working with them. You don't believe me, but I was working with this magnetized like this for a very long time. And I kind of get over the frustration of being magnetized like this. I had only this core alone by itself without any coil on it, and I had separately the coils, the wires. As you can see here are different. There are actually 4 or 5 types of thickness of wire. As you can see here, it's very, very thick. You see, it's very thick here. This one that is coming from inside, and this wire is stick to it, but this is the element that is coming from inside, very, very thick here. And as long as I'm getting outside, I'm putting thinner and more thinner wire. And this was a very weird lesson for me. This is actually the 3rd or the 4th bobbin or electromagnet, if you want, or the magnetizer that I build, or that I put the coil around it until I figured it out. I didn't know how to build it. I had absolutely no idea. I look on internet, nothing about it. I also speak with people in forums, in my favorite AAC forums from from the internet. They come with some theories, but a specific way to do it, how to do it, nah. So I had to try it myself with my knowledge that I had, and my knowledge about coils and electromagnetic fields, electromagnet, because this is an electromagnet. What I built here is an alternative, is powered from alternative current. It's not a DC, it's not a direct continuous power, is alternating. That is, but it is nevertheless it is a electromagnet, and it's I didn't know how to make it. First of all, this is the first one that I ever built in my life, and I had to struggle to find a way. And the first demagnetizer that I built, like I said, this is the 4th or 5th version that I'm having right now, that I'm presenting it here. So the first one was only this coil in the middle without anything outside it, like I built here. And that one with so few coils around it, I put it directly on my 240 volts there. All right. Can you see the smoke? Is very, very thin smoke, but it's there. It was a bit more consistent, the smoke. Yeah, you see the flame? And I can actually smell it. Huh? Yeah, you can see. Can you see the smoke? It's emitting a tiny little bit of smoke. Yeah, you see it? Now you see white smoke, very thin white smoke, but it's there. So this is my test at direct 240 volts AC right now with this switch for on off. So this is the experiment. So this and this is very very hot, very oh wow, it's very hot. Probably no, it's very hot, super hot, super hot. Here, woo, probably more than 50 degrees Celsius here. I cannot keep my finger over it. Yeah, it's starting to burn me. So around 50, but the interior is becoming extremely hot. The exterior is a bit more colder. So here in the interior is super hot. My suspicion is because I used like 5, maybe 6 types of wires, very different diameter wires. As you can see, this is the first coil of wire that I use, very thin, but I have even thinner than this size that I'm using there, and then very thick here on the exterior. And you can see one type of coil, which is not this one. This is the first, then probably this one that you can see it here, and then very extremely thin that is around, and that's where you've seen the spark and the smoke coming from. It is my best guess. It's from that very extremely thin wires that I used, coils. So my impression is that they are acting like a very thin fuse. Because they are very thin wires, they probably act like a fuse. Is the best explanation that I can think of. Every wire that I'm having here is scrapped from God knows what. Over the years, I accumulated it and store it somewhere in a bag. And now it's time to actually fucking use it. And I know this is a big problem using scrapped wires. This is first very bad element to use it like that. But theoretically, not every scrapped wires you get that bad luck to short it if it's not really a problem all the time. It was scrapped, but in relatively good condition. This is looking like it's brand new. This aluminum red coated isolation wire that I'm having here. This is looking like brand new, and it feels brand new. From a coil from a CRT computer monitor. This was the coil around the TV screen, and I take it from there. The rest, God knows where I have it. I have those coils. They are scrapped. It's like that. This is a big mistake. This is a big problem using scrapped wires. But I'm counting on the good isolation for the rest of the wires that I'm using. Use it like that, as bad scrapped as it is. So this is my experiment so far. It's working fine at 24 volts AC with my variac there. It's working absolutely fine. It's like 10 seconds until it's getting warm. I'm not sure hot. I believe it's like 15 seconds or so. So very, very slowly it's getting hot and warm. So I can actually make a lot of... I actually demagnetized my tweezer and a couple of needles that I was having, sewing needles that they were magnetized. They get magnetized all the time because I'm keeping them here in this box. I have these 2 magnets here specifically for this needle, but my sewing needles that I'm having there are in this little box. It says there here in Romanian, needles for sewing, pretty much to translate it to you. So they are here, and they get stuck on that magnet and they become very, very strongly magnetic, and I really don't like that. And other little things that I'm having here, like this one as well, is becoming magnetized. Sometimes they are catching there like that, you see, and because of that little shit there. That's the cause for this project. This is that's the motivation to build this coil and all this thing. So my intention is to take out all the coils that I used here. Like I said, those 5 coils, terrible. A couple of them are terrible small diameter, very, very extremely thin wires, and rewind everything with this thicker coil that I'm having here, and especially in the center. In the center, theoretically, I'm thinking to add more thicker wire in the center here, because here is the strongest field, and the bigger the coil diameter, the better probably. This is my idea, but it will occupy a lot of space very quickly if it's too thick. I'm not completely sure what to do. And then to pile up, to add this rest of the coil. And I have a ton of coil here. I specify this. I'm building this coil. I'm winding like a Neanderthal, without thinking, without counting, and pretty much by the ear, if you want to, because my reference is not how many turns of coil I'm adding, because this is a very weird diameter what I'm having here. It's not even a circle; it's an oval, and it's probably a very hard math to do. And I'm definitely I'm not I'm not a math person at all, and I'm doing it by the ear. And the most important reference that I'm checking and that I'm comparing with is how hot this thing is getting, how strong the electromagnetic field is creating, and at what voltage is actually working without overheating. That's my only point of reference. The number of turns, the size and the shape of the turns doesn't matter. Doesn't matter where I'm putting them. Here in the center, as you can see, around this middle element, and then around it doesn't matter. All that matters is the heat, the electromagnetic field, how strong it is, and the voltage, not to overheat. So my target, this is actually a success what I'm having here for 24, like I said already, for 24 volts from this variac. It worked absolutely perfectly. Good time, very good time of overheating until is overheating. So like 10 or 15 seconds until it's getting hot, and not from warm to hot like that. And plenty of times to make multiple tests, multiple demagnetizations runs. I actually demagnetized a couple of needles that I'm having there, including this tweezer, both its legs. So it's actually theoretically is working fine, but at 24 volts alternative AC. My goal is to use 240 volts AC because it's easy to plug in and to plug out, and it's very versatile, and it's looking like it's more a professional design, a professional tool to use when you plug it in 240. No business, you know. And yeah, that's my goal. Let's hope I can actually de-wind everything, get it back to its core, and rewind again. Yeah, that's it. Thank you very much. All right, I took out the coils, and this is how it's looking without the coils. This was the first one, as you can see, is way blacker, and it's very scrapped. Everything I have here is scrapped. So this was first, this was second, this was the third, fourth, and fifth one. So this, and you can see how extremely fine is this one. This is the finest. And let me actually show you how you can see the burn marks from this coil, because this and this one were here in the interior around this core, and probably you can see it a little bit yellowed, especially here in the middle. Here in the middle is a little bit yellowed from this core, which was the first one, and is definitely more burned. And this one as well is very burnt. And this one was, so these two were on this core, but this very fine one was around, was the first one around, and it was staying close to this, to burn it, to actually get the burn from it. And this was the second on top of that, and this was on top of everything. I could clearly feel a very strong heat coming from here, from the interior, probably from this, and especially from that. And that's more like a fuse, as the scene it is. Yeah, very interesting. Yes, I'm always forgetting that I'm actually having pictures, and one picture is like 1,000 words. So I will get over everything very quickly. These are the cores that I salvaged, and I had them from my adolescence, very long time ago. Here actually is the data about them. So A is the height, here the height of the core, the middle core, 20 millimeters, 14 millimeters is B, which is this side, and C is this 9.5 millimeter. And then this is the I core here, this ones, and these are the data about it. Here is the A, B, and C size. This is the first coil that I actually made around this I core, and I actually put it to 40 volts. If I remember right. I don't really remember what I did here at this stage, but it was the first one. And you can see this red line. This is the coil, the actual coil here beneath this isolier band. This is my fuse. You can actually see the wire. This is the wire between two screws. That's my homemade fuse, and it saved my ass unnumbered times. It's very good. All right. Here I made another one. Did test it at 240 volts, and with this one I made the short. So this fuse here blow up with this coil that I put it. This was the first test, and I was actually counting turns, how many turns, and then I give up. Okay. My test bench 240 volts mains fuse who covered my ass in unnumbered experiments, and it's very true. Right, this is getting serious with the core. When I started, this is the second, probably the second version, and is the one that you've seen already. And here I tried some gaps between the cores, but it didn't work at all. And this was another version actually, one of the first versions. This is how I plug it in to 40 volts in this stage. How many windings. Do you see how many windings it's having? And with this one, I didn't make a short, but it did heat up like in a fraction of a second, like 100 degrees Celsius, very, very quickly and very hard. It heated up like this. Actually, the string wire, this black string wire melted, or I actually get a white smoke from this string wire that melted from the heat of the coil in a fraction of a second. And then I deduced that I probably need more wire, and this is my resolve here with more wire. And this didn't blow the fuse, but also it got extremely hot very quickly. And then I decided, and this is the original scrapped wire, this red scrapped wire that I had, untouched. And I just, here I just measure it with my caliper, and it's 0.6 millimeter in diameter. I measured the diameter of this wire, and it's aluminum, as you can probably see, is very white here. And here is around everything, because I didn't have any kind of space. Here I decided to go around everything, and I hook it up to 40 volts, and it was still heating up very quickly. Here is in the middle of the coil. When I was testing, I just peel off the isolation, and I made the test there. And here is with the entire coil, and I was so sure everything will work fine, and it didn't. It was still heating up like very fast. This is another experiment, most probably. This is the burned wire that I had. Yeah, probably exactly after I got the sparks. And yes, okay. So here I was winding back everything that I built there. So this is from the big. This is the last coil that I have right now on my table, and I will show you in a moment. This is how the beginning of it. What is containing internally this very thick wire that you are seeing here. This is from the front. And this is another wire on top of that, also very thick wire on top of that very black one here. Yeah, probably the same. And this is its end here on the top, very exposed. And here I started to add this red wire on top of, in between this, in the middle here, as you can see. And I link it there. And then I started to add it around the core, because I didn't have the room here to add anymore. And here is how uneven everything was. How it was starting to look about. So as you can see, I started with very thick, and then adding a smaller diameter as I was adding in the exterior of the bobbin, like this, like this, like this. This is the cardboard thing, like this on top, and I put around it. It was smaller, and I had to make it even bigger than this. Yeah, here at this point I did make another test, probably at 240 volts or at the 25. I believe at this stage I made it at 25 AC, and it worked okay, but it was still heating up. And then I decided to add this other. I already added this coil here, and then I decided to add this other thing that I'm having here, another round, and is here already. Then I tested with 500 ohms, because I put them in parallel. The resistors got extremely hot, and I give up on adding the resistor. At this stage, what you are seeing here, you see I've added this larger cardboard here, and all these wires that you are seeing. This is the final stage that you are seeing right now. And I didn't test it at 240. I only tested at 25 volts AC from my Variac. That's it. Right. Actually, I use this testing wire that I'm having. Here, theoretically, I'm having a fuse that is never blowing up, unfortunately. But this fuse, you can actually see the wire inside there. It's two screws. Here is a screw, and there is a screw. I will probably have to present it sometime. So I cut one wire from this cord line. Is having 3 wires, and one wire is connected here in this screw, and in the other part of the wire is here connected on this screw. And between these two screws is that you see very fine copper wire. That is my fuse. Always, all the time, this fuse is blowing up when I'm doing something stupid. Unfortunately, this didn't, and I have on 2 sides 2 fuses here, and it never wants to blow up. Came back to my original idea. When this was having a little tiny bit of coil, I took this testing wire. I soldered those 2 wires from the coil here, and I plugged this one in the 240 volts, and from here, pack, like this I was doing, exactly as you are seeing here for a second. And 1 second and back. And this is the movement that I'm doing when I'm testing. Very quickly. Pack. In this pack time, it's probably 1 second or 800 milliseconds, maybe very close to 1 second when I'm doing this movement here. That fuse there blow up. Also, this coil. Well, not this one. The first one that I built with a very thin coil in the middle. It was super hot, extremely hot. in only 1 second, 800 milliseconds or something, a little bit less than 1 second. So that was, you know, very, very disappointing for me, because I didn't know how to tackle with it, how to manage it. And then I got the idea to add more coil to it. Then I had the idea, let me put around the entire element, this core, around it, not only in the center but around it as well, because my idea was that the current is moving like that, and after I finished here, the current is still going in the same sense, in the same direction as the one that is in the center here. Here is very concentrated in the middle, is very forceful, and around it is getting weaker and weaker. Well, the current is the same, but the electromagnetic field, that sense of wiring that I did here. So that was the idea, and I put literally all these wires that you are seeing here are scrapped, and some wires are looking like they are brand new, and some are completely or partially, or they have a good amount of burn sign on them. You see how beautiful concentrated color is having. Usually this is the color that a good wire should have, that is not stressed, that is not burned or overheated. When it's starting to get black, then is a shitty wire. Let me actually show you. So this, I actually put these wires here in this bobbin. This I tested with this very thin, extremely thin wire. You can barely see how thin this is. You see, this is the wire actually. You see, it's very, very, very thin. And this is a bit more thicker than this, but still it's very thin as well. This is very burned wire, and this is partially burned, or like I like to say, is stressed, is thermically stressed, this one. But this is definitely is burned like shit. And I had problems in the sense that I had sparks. When I tested after that, I believe I was still testing at 240 volts directly, still doing this thing here. I was having way more wire, and the second, when I've added a lot more coils, a lot more wiring, but to this coil, that fuse didn't blow up anymore. But the entire coil that I'm having here was getting in 1 second, in less than 1 second, this thing that I'm doing, that I'm showing you right now, one and back. And the coil was boiling. It was super hot, like probably 100 degrees Celsius, or 200 Fahrenheit, if I have to convert it. That's the problem with coils at alternative current. So this was my experiment. That I really don't know how to do it, to make it work. I did manage to make it work actually, but I had to experiment a ton of ways. So I had to get out of all of these windings that you are seeing here a couple of times and rewind again, following different logic. And one important logic that I build, this last one that you are seeing here, is, like I said already, very thick wire inside in the core here in the middle, around the middle here, very, very thick, and then thinner and more thinner towards the exterior. And then I tested, this one I didn't test it at 240 volts. I actually used my variac. Let me show you. That's my variac, and I switch it to 24 volts. Why 24? Because it's 10 times less than 240 volts from the mains. So that's the logic that I use. And I'm having it written here actually at 24. Very quickly at the very end, I actually tested at 30. Usually, what I test, everything that I build, all the other versions, I test them at 24 volts, AC alternative directly from that variac, and that helped me to realize what I need and how to build it better. I still use exactly this wire, testing wire that you are seeing here for the variac. You see this plug? I'm inserting it there, and then I'm doing exactly the same thing as with the 240 volts. I'm moving, I'm clicking like that, and very quickly, like one second, less than 1 second. And that's the biggest problem that I had with this was heating up. And also the electromagnetic field that was created was weak, depending on the voltage that I was using. How high or how low the voltage was. If I was testing it at 10 volts alternative, the electromagnetic field, I could barely feel it in my tweezer. When I'm passing the tweezer to demagnetize it here, it was, this is vibrating near the core. And usually, and it didn't vibrate at all. But at 24, it did vibrate a tiny little bit. You know, it was enough to feel the vibration and to know that something is going on there. And that is doing its job. And then this magnetic field is directly proportional with the temperature. This coil is getting higher and higher as the time is passing. So remember the first experiment that I did when I had a little bit of coil and I put it directly on 240 volts mains. It got hot, 100 more than 100 degrees Celsius in a fraction of a second. Here with 24 volts AC, or even with 10 volts AC, is getting hot, but not as quickly. It's like 5 or 10 seconds has to pass, and then it's getting warmer and warmer, and then it's getting hotter. And if I leave it too much on, it will get extremely hot, and I don't want to risk to burn something, you know, especially this amount of quite good, quite new coil that I'm having here. All this experimentation, it took me 1 week, 2 weeks maybe, of a lot of frustration. It's very hard to de-wind everything and rewind it back and test, and holy fucking shit, you have no idea. I did it manually, everything. I didn't have a device to do it automatically, so I did everything by hand, and it's not nice. It's not nice, and I had to experiment, especially with this cardboard insulator that you are here seeing here. This is very important, this insulator, because the wire will make sparks with the core if the enamel is in direct contact with that thing. It's from my experience, but probably I use some very scrapped and very black wire that you've seen. Which one? Here. Probably this very scrapped, very black wire. And I had this one and one or two other also very fried wires that I used in my testing, in the believing that if it will short, it will not be a big deal because it will act as a lesser wire, because I'm having a lot of wire already, so that will not really matter that much. But it did matter because the thinner the wire, the more resistance is opposing, and it's heating up very quickly. That's the problem with very thin wire. And the thicker the wire, this is my conclusion that I got after playing with this kind of failed experiment that I'm having here. The thicker the wire is less resistance and is getting warm or hot, not so quickly, is elongating. The time have to pass a little bit until this thick wire to get warm or hot. So, but I did put this thinner wire, and I have, like I said, 4 different diameters of wires, because all the wires that I'm having are scrapped, and I don't want to use brand new wires. I do have some, but I don't want to use them, especially for very weird experimentations like this one. This is a weird one, and it didn't work as I expected, and yeah, it did teach me some undesired lessons, and I had to include this kind of failure, because this is actually working. And let me actually demonstrate that is actually working, but I will have to be quick about it. Like I said, it is getting hot, and I have to actually prepare it here. Okay, so there it is. This is 24 volts set up already. The switch is off. You will see the LED. Hopefully, this LED will turn on. You see, when it's activated. And here it will not show anything. And let me hopefully turn it a little bit. You cannot hear it or sense it, but it is vibrating the needle a little bit. Actually, I can show it like this. Yeah, see? Yes. It's a tiny little bit, it's not that strong. And I will have to wiggle to move this around a little bit in this field to demagnetize it. The space here from cardboard is a bit too high, and it doesn't let me hold this needle too close to the thing there, and to make contact perfectly, so I have to incline it like that. This is highly magnetized, this one. Let me bring another magnetized needle, hopefully. Yeah, you see, it doesn't catch it. It doesn't catch at least this side. This side, okay. So I didn't show when it was magnetized. I should make a test when they are both magnetized. Yeah, this one. See, this one is highly magnetized. So let's do this. Okay. Yeah, see, and it did its job. It did demagnetize it. And on this side, it is magnetized. Not really. Not really. Yeah, okay. So it's doing its job. Let's see. But you must have a special setup for it, and this kind of you must have a variac like this, and it's a pain in the butt. I don't like it because it's not that general purpose, and I really wished to build this for 240 volts directly to the mines, to be standalone. You know, you plug it without transformers, without anything else, and without any other kind of power supply. Except itself, you know. So that was the big disappointment with this version that I'm having here. It is doing its job. It's good enough, but so in a sense, this is a success. This is a workable element. I managed to make it work, but it's it's good as a project, but it's not cheap. It's not cheap at all. So if you have this kind of core lying around, and you have a ton of scrap wire that you scrap it from whatever, this is absolutely a perfect project for this kind of stuff that you gathered, and you have it around. Let me actually let me actually show you. This is the cardboard core of the wires that I used here, and this is how I'm keeping my scrapped wires. As you can see, this is very burned wire. This is absolutely burned. I'm not completely sure if this is actually burned or if it's is good enough, but I know for sure this one is very burned. Comparative with this one, you see how shiny is this one and how burnt this one is. So this is how I'm keeping my scrapped wire from. I don't even remember from where I have this scrapped wires, and from miscellaneous, you know. And it was the same thing for the wire that I'm having here. So if you have a spare scrapped wire put aside, like I just showed you in my bag there, this is a perfect, absolutely a perfect. It is a genius project to use it for a demagnetizer. But unfortunately, me personally, I don't know exactly how to make it work directly at 240 volts without overheating. First of all, because this is the main problem. Here at 20 volts AC, I can keep it like 10 seconds without overheating too much. This is the major, absolutely the major problem for it, the overheating and how big the electromagnetic field is creating to have a workable demagnetizing field to actually do the work, you know, to actually demagnetize the steel the tool that you want to demagnetize it with it. And it's a very thin balance between voltage that you have to power it with, especially the alternative voltage, that because this must be inside an alternative, it must be powered with alternative voltage. That's the working principle for this. If this is powered from a DC current, it's just an electromagnet that is sucking the instrument that you want to demagnetize, and it will magnetize it. Actually, you will convert all of this into a electromagnet or a fixed magnet, polarized magnet, pretty much. And one single pole will actually magnetize your instrument. And using AC, alternative current here, is actually fluctuating is changing the polarities, positive, negative, and then positive, negative, you know, and then positive, negative, and so on, and is rotating the positive and negative, you know, the sinusoid, and it's creating an alternating magnet at very fast speed. And if it's fast enough, it will demagnetize the tool that you have. That's the working principle. And like I said, it's a very thin, like ice thin model to work with. This entire object that I'm building here is like a thin ice. You have to equilibrate the voltage that is working with at AC voltage, of course, the strength of the electromagnetic field, and the number of coils, and the overheating that is emitting. So it's a very thin ice. You have to balance everything just to be right. And this is my solution that I find it experimentally, and a lot of many days, actually, like 2 weeks I stayed on it, many permutation, many tryings, a lot of fucked ups, like the fuck ups that I did with directly at 240 volts with very thin wires. So that was a very big mistake, but fortunately, I have that very trusty fuse that I built there, and that one saved my ass a lot of times, actually. That's why I'm permitting to make stupid mistakes, because I know I have my ass is covered. So this is it about this demagnetizer solution that I'm having here. So next, after this fiasco, because this is not really a reliable tool to use, and not everybody can actually build it and test it like I have my meanings here. Not everybody is having a variac or variable transformer. Variac, this is what it means. And also not everybody is having a lot of spare coils to test with. So it is a solution, but not quite really. Theoretically, if you have a transformer and you get 20 volts or 15 volts or 25 or 30 volts from that transformer, theoretically you can power all this thing to that transformer. But depends that transformer, it must be quite powerful, because this thing will eat a lot of current and you can actually burn the transformer. So but it is an idea. You have to test everything and see how, number one, how hot everything is getting. If this one is getting hot, or the transformer that you are using is getting too hot. And luckily, very luckily, this coil devices, they are taking time, a little bit of time to heat up. So you can actually test a little bit, then unpower everything, test for temperature, how hot they are getting, and if after 1 second of clicking, you know, of testing, if it's still hot, if it's getting warm or hot, then you have to change some parameters. But if it's still cold, you test it for 5 seconds, then for 10 seconds, for 1 minute, and for a couple of minutes, and maximum 30 minutes or 10 minutes maybe. Leave it on all the time, you know. But generally speaking, you know, for everything, in my case here, it was enough, like 10 or 20 seconds for this, because I'm doing it a couple of times the demagnetization. I have to switch around the tool because here is another problem with the magnetization, with tool magnetization. It gets some. Let me actually draw it for you. So if this is my tool here, so it's like this, you know, and like this. So this is my tool, and like that, and is getting pockets or areas of magnetization. So this is the magnetizing spots. Here is not magnetized at all, but here it is. Here is not magnetized at all, but here it is. You know, and somewhere there, like that. So there are like little islands of or spots of magnetization, and you think on this face, you clean it. You know, you move it into the magnetic field there, you demagnetize it, and when you test it this side, nothing sticks to it. But when you turn it around, you test it again, the thing is magnetized. So this happened to me quite a lot of times while I was working on this project. This happened to me. Probably also different strengths also. So this will be plus plus, this will be plus 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 plus. So very strong here. This will be only plus one single plus, which is very weak, medium strength, and this will be extra mega strength, depending where you keep your tool. Sometimes I'm touching it without thinking about to a magnet, and depending the area that you touch it to that magnet, you know, the area of contact with the magnet and how strong the magnet is, and probably also the imperfections in the entire tool that you have are determining how strong the island is getting. So it's not cool. It's not nice. So you have to be aware of these little pockets or islands of magnetizations, and you have to clean them all the time. You have to do this. So, and for this, you need time. You need time to test the tool, and to test the tool multiple times actually on both sides, on all its sides, and after you test it, to demagnetize it again and do multiple demagnetization. It's not only one demagnetization, that's all. It's not like in movies. In reality, it's a little bit more shitty, way more shitty, and that's why I like it. All right, so that's with this tool. And I speak about it too much already, and that's it pretty much. And then after a couple of days, actually today, I built this one, and what I'm having here, I'm having 4 permanent magnets. You can see them. Actually, I can show you. Like this. This is a motor, a simple motor. This type of motor was used for magnetophone, cassettophone types back in the 90s. You know, boombox they were called, or something that this was having. This was rolling, moving the cassette that you are playing. You know, it says there 9 volts DC. You can see it here is working for 9 volts DC. This is a serial number, and probably this condenser or this capacitor that is still here was original on the board that I scrapped it, and I preserved this capacitor on its legs here. It's having very strange noting, the notes that it's having here. Let me actually zoom into it. And you see there, it says A, B, positive and negative. Very strange markings. I'm not familiar with this kind of markings. I don't know what they mean. The positive and negative is just a coil, and if you flip the positive and negative, it will run in one sense or in the other. So right now, I actually test this motor, and with the current setting, the current wiring that I put here, here it says the negative here, but I put the positive wire. This red wire is the positive, and I'm collecting the negative from this other pin that is on positive, because I actually tested it with my variable power supply there. I can see how much current is consuming, of course, without this capacitor when I tested it, and I was seeing how much current is sucking, and also how fast is turning. In this configuration, with these wires that I'm having it here, is more faster, more powerful, and is consuming a little bit more amperage, like 200 milliamperes or something. The same voltage at 5 volts or something that I tested it. But if it's in the correct specification, positive here and negative here, so inverse, the wire is very weak. So probably it's having an internal circuit there, some chips or something. I have no idea. I never disassemble it, so I really don't know what is inside it. And then I put back its capacitor corresponding to the wires that I'm having here, negative on this wire and positive here for the capacitor, to be correct, not to explode in my face. And that's it. It is working without the capacitor, but I leave it there just for kicks, just because it's looking cool. So about this thing, I actually it hit me one day, this little plastic piece that you are seeing here, because let me show you. I'm having different plastic types of plastic, and this is HDPE, or PE. HDPE, it means high density polyethylene. So this polyethylene plastic is what I build this element that you are seeing here. As you can see, there are tiny bits there, little cut bits that I cut them with this with a scissor. As you can see, I cut them in square shapes, to be easy to to grab them with my heating iron. So with my heating iron, I'm grabbing this little bits of plastics, and I'm adding them one on top of the other, and I'm making like a mush, like a smudge. Well, I'm adding, and I've added a lot here a couple of times, and actually, and I wasn't sure if this was a good idea, because when I had to put the magnets here, these are the permanent magnets that I inserted there. When I had to insert them, if I'm heating up the magnet, it will destroy its magnetism. Pretty much, it will become a worthless piece of whatever material is here, ferromagnetic element, and it will not have the magnetism of a neodymium like it should have if you heat it up. So so in the end, I decided to drill the holes and press fit this little magnets here. It's not perfect by any means. It's not perfect, but it's good enough. You know, it's good enough. Like I said, I was questioning the path that I took it to melt all this plastic and to form it like you are seeing it here. But it paid off, because at a moment, I'm not sure how well you can see, but here is a barely visible line. You see it here. So before, I was having it this thick, and then I've added a little bit more on top of it and reshape it again and make it flat and everything, because the original thickness, the magnets was too high, and they were getting off from their holes. So I've added a little bit more material, a bit more plastic on top, a second layer here, and I heightened the thickness. I make it more heightened, and now they have a little bit more space to get deep into. So it was a good decision after all, and I had to drill again. Here it is. This is my machine to drill the holes with 5mm drill, and press fit this again, and that's it. And it's working. Actually, this is the best idea ever. It's the best idea ever for a demagnetizer, and I love it. And it's quite smart. It's a way more better idea than the one with the coil, because you can use whatever transformer you have, whatever motor you have. You can use even a 240 volts motor if you are crazy. But there are small motors like this that are running at 240 volts quite fast. I'm running this one not at 9 volts but at 5 volts or even 3 volts, and it's doing the job. It's doing the job. This demagnetization thing that I'm having here is doing the job. And the logic that I actually marked with color here. See, I marked with color this blue and this orange, because as you can see, I'm having this blue bits and this orange bits, and this white thing is the core there, so the meat. And I marked the polarity of the magnets. One is south pole up, this is north pole up. South pole up, north pole up. So it's one, and the other is inverse. You know, one is with one side, the next one is with other side, and then so is alternating the polarities of the permanent of these permanent magnets. And you can check them, actually very easy. You can check them if they are sticking together like this. They are on the same face. When you put them side by side, they are on the same face. This is north, this is north. Doesn't matter which is north or south. I have no idea which is north or south. What did matter is to be the same polarity, and the other ones to be inverse from the ones that you put them. So if they are stacking together, you put them side by side, and they are having this top face, and this top face is one polarity, is the same polarity. And you press them down, and then the others, if they are glued, if they are stacking on these ones that are already mounted here, you switch it like this, and you press it down in there. And on this last one, if this one is stuck like this, you drag it like this, and you press it down, and it's the same polarity with this one. I hope it's making sense, my logic that I used here, without using only these guys that I'm having here. Let me actually show you how thick they are. And this is a hole that I used, that I made with the needle. Yeah, you see, this is how thick they are, how thick it is. I have bigger magnets, but as the bigger they are, the heavier they are. So oops, I don't know what polarity I'm having here. As you can see, it did stuck on this one. So if it's stuck on this one, let me actually show you here like this. With this face, without turning it, I'm putting it here. So like I said, if this is with this face and this is stuck with over this, I'm moving it and pressing it down. That's what I did here, and it's the same polarity with the opposite side, and I know it's correct, and that's it. This is the thing. Of course, I didn't have to add this polarity, but it's easy for the movie to show you in the movie the principle of working. And when it's rotating, is alternating these polarities, these poles, and is doing actually a very good job. And let me actually demonstrate you. All right, so I purposely, like I said originally, let me actually power up Yeah, you see, it's 5 volts instead of 9 volts. And I will probably lower it down. The good thing about this motor, or a small motor like this, powered from, yeah, I will power it down like this. Yeah, you see, 3.5 volts with 80 milliamps. So that's, I lower it very much, the power, because I really don't need to be very fast. It doesn't matter how fast it is. This speed is good enough. So as you can see, let me test with this guy here. The good thing about this motor is that it's powered from a very low voltage, very low power consuming, and very affordable power supplies you can use for this. And it's also very small dimension, and it's doing perfectly the same job as that big shitty coil that I wanted to make. And yeah, that was a fuck up. A very good thing is you can run this for a very long time. You can keep it powered to spin, and you can take your time with it. You are not forced to move quickly about it. You know, that's a very important thing. And it is still magnetized. Probably it's is the tip of this canife. Yeah, you see, ta-da! Yeah, that is an island of magnetization on the needle. But here, yeah, for a little bit, for a brief moment, it wasn't. Yeah, it's probably having a little bit of islands. I actually demagnetized everything. Everything you see here, it wasn't magnetized like it is right now. Now I purposely magnetized them all. Let's see. Let me actually put them there. Yeah, it's still magnetized, motherfucker. Actually, maybe it's a good idea to do it like that, like this, because it's a very strong field here. Like this. Let's increase a little bit the voltage, not much, to 4 volts, and the speed is a little bit more speed. And as you can see, it's taking a little bit of time. Yeah, these motherfuckers. Yeah, you see? It loses its magnetization already. And voila. And voila. Isn't this cool? Isn't this cool? Here's a little bit of magnetization, probably. Yeah, in the tip of that needle. So this is the biggest problem. You don't know which one is magnetized, this needle or this instrument. Probably this needle is still having in the, like that. I'm actually touching the surface that is spinning. And let's see, are you, no, it's still a little bit, probably this time maybe saving a tiny little bit. Probably a tiny little bit of island, magnetic island, probably, I'm not sure. But it's definitely very workable right now. It's absolutely fine. My tweezers, my tweezers, both of them, you see, both of the ends of the tweezers are magnetic, and probably it magnetized the needle as well. So like that, voila. Nothing, absolutely nothing. How cool is this? How cool is this? I really like it. I really like it. Very small dimension, variable speed for the rotor. The magnets are not flying off from the case, are not sticking to my instrument here. It's very good. It's very good. And I'm suggesting to everyone to build such a very cheap, very cheap and very affordable little demagnetizer tool. And yeah, it's way better than my previous shit that I had. So these are the other needles that I'm having in stock. So this tool, let's see if this is magnetizing this one. No, not really, not really. Let me check it like this. Come on, you are not magnetizing shit? No, nothing, absolutely nothing. Excellent. This is what I wanted. Exactly, this is the effect that I really wanted, and it's very good thing. Actually, let me actually, you know what? Let me actually grab all of them like this. Nah, and move them like that, and this one. And this one, and ta-da! And remember when they were sticking all together, and now they're just flying around. You see, this is exactly the effect that I wanted it to obtain, and this is the exact behavior that I wanted to get. So it's a very cool demagnetization tool, very cool to have, and a little bit, you know, I had to spend a little time of melting the plastics until I got this shape that I'm having here. to calibrate it, to actually make it as I wanted, and in the end is perfectissimo, perfectissimo. All right. Pretty much this is it. Yeah, I'm very happy with this project, with this demagnetization project. I'm very unhappy with the demagnetization coil that I really tried. I really tried my best with the limited knowledge that I have about coils and electromagnetic fields and the core and transformer cores. I really didn't work that much in my life with them, and I'm really disappointed that I couldn't get the effect that I wanted, this effect that I'm getting with this very cheap alternative. This is a very cheap alternative. So mechanical alternation of the magnets is the key here, and not electrical, unfortunately. Yeah, it can be made electrically, but it is suffering. It is suffering from overheating, over voltage, dimension, too big dimension. I'm really disappointed on that idea, but I'm really proud on this one. I'm really proud on this one. It's very good. All right, thank you very much for watching. That's it for this demonstration and for this experiment and for this project. This solution is very miniaturized, and I really like that it's very small, and I can actually store it somewhere as it is, as you are seeing it right now, and actually write on it demagnetizer, and I know exactly what it's doing, and also the voltage that is working, the range of voltages, because I can fluctuate it. Right now is at 4 volts. You see there, 4 volts. And thank you very much for watching. Thank you very much for liking my videos, and see you next time with the next project. This project is finished here. Bye bye from your favorite artist and friends, Mr. Q12. Bye bye.